part 2 of the derivative of trig functions. All right, last time we left off, we showed you the derivatives of some of the basic trig functions, and we did some examples. Got one more example for you that's just with the trig functions. I got 2 application problems. All right, the other video is getting long, so I decided to separate it into 2. So let's look at this young example here. I have the derivative of sine of, 2x over x plus 1. So I've actually got another chain rule, all right, because my outside part is the sine function. All right, but the inside part in here is now an ugly 2x over x plus 1. Okay, so my inside part, I'm going to have to deal with some quotient rule. Well, let's just attack it. I mean, there's nothing else to do but just attack it. So let's do it. Find the derivative of this function. All right, find the derivative of the outside first. The derivative of sine, if you remember it, hopefully is cosine. Leave the inside part still there, 2x over x plus 1. That is all the derivative of the outside with the inside still there. All right, now we need to attack this inside, okay, because we're going to multiply this by the derivative of the inside. All right, so the derivative of the inside is going to be a quotient rule. Low d high minus high d low all over low low. All right, so let's work it. The low is x plus 1. The derivative of the high, so the derivative of 2x is 2, minus the high, which is 2x, times the derivative of the low, which is the derivative of x plus 1. The 1 goes away, the x goes to just 1. All over low low, so x plus 1 squared. Wasn't too bad. We just got to clean it up now. So we got the cosine of this 2x over x plus 1. All right, we clean this up a little bit. All right, at the top, when you distribute through there, it's going to give me 2x plus 2 minus 2x, if I did that right, all over x plus 1 squared. All right, the 2x and the minus 2x actually cancel out, so you're going to be left with, in some form or fashion, cosine of 2x over x plus 1 times 2 over x plus 1 squared. All right, and that's it. Okay, one important thing to notice here. All right, this first parentheses means it's the inside of the cosine. The second parentheses just means I'm multiplying it by this. All right, so don't try to multiply these two things together and get like 4x over x plus 1 cubed. Okay, no, because this first one is stuck inside the cosine. It's not the cosine of both of those parts. Okay, in fact, it could be rewritten as the 2 with the cosine of that 2x over x plus 1 all over x plus 1 squared. Yeah, but that's a little ugly. So this is totally fine. Just realize that these two parts don't actually mean multiplication. The first parentheses means it's inside the cosine. All right, now for some applications. Okay, a couple different applications we have are springs, and then we'll see electrical circuits in a second. All right. Suppose that U of t measures the displacement, measured in inches, of a weight suspended from a spring t seconds after it is released. And that for this particular spring mass system, U of t is equal to 4 times the cosine of t. Okay, this is just an example. So what we got going on here is we've got a spring. I meant to do this at the first part. Okay, I've got a spring, all right, with a load attached to the bottom of it. Okay, At some point, it's an equilibrium point. All right, but up here it's not because it's going to drop. All right, and the spring is going to go up and down and up and down and up and down until finally it probably doesn't come to a rest because of forces like gravity. Okay, but before that, okay, before it stops, it's going to do what? Go down, then up, then 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 down, then up. That's actually a periodic sinusoidal function, which trig functions like cosine are great representations of. Okay, so that's why it is what it is. All right, so the question here is find the velocity at any time t and then determine the maximum velocity. All right, well, if this is displacement, okay, kind of like the position function, then if I find the derivative of displacement or function is going to be velocity. So really all I got to do is find the derivative of this function here. So if the u of t is equal to 4 times the cosine of t, sorry for using t, but t stands for time, so it makes sense. When I find the derivative, okay, and that's going to be the velocity. I guess you could say this is the v of t, the velocity. It's the derivative of the displacement. The 4 is a coefficient, so I'll leave it. And the derivative of cosine, hopefully you remember from the last lesson, is a negative sine. Clean it up a little bit, we get negative 4 times the sine of t. All right, and that's going to be the velocity at any time t right here. Your v of t is this function right here. All right, for the second part, it asks to determine the maximum velocity. All right, the fastest it's ever going to get. All right, and we can tell that by realizing, hey, what does the sine function look like? Or more importantly, what does a negative 4 times the sine of a function look like? All right, well, sine starts at what? 0, 0. Normally it would go up to 1 and then down to negative 1, then up to 1, then down to negative 1. All right, but the negative 4 means it's going to go down first and then up. And the 4 tells me the amplitude, so how far up and down it goes. So this actually is going to go down to negative 4, and then up 2, 3 to positive 4, and then down, and then up, and then down, and then up. And in a perfect system, it will keep on going up and down forever. Of course, probably because of gravity and stuff like that, it's going to slowly, this curve is going to start going in on itself. But regardless, the maximum velocity is going to happen where this velocity graph, which is this one right here, reaches, or it's going to happen at the high point. All right, so the high point here, I just said just a second ago, because 4 is the amplitude, is actually going to be 4. Okay, so the maximum velocity is going to be, well, we're measuring the displacement in inches. The max velocity this thing will be going is going to be 4 inches per second. 4 inches per second. All right, we can actually do a little bit more thinking here and figure out where that occurs. All right, 4 cosine actually starts up at 4, then comes down, and then goes back up. All right, and actually where that maximum velocity occurs is when that spring is in its equilibrium point, okay? At the very end, it's going to rest somewhere, okay? But if I bring it down or I drop it from up here, okay, it's going to reach its maximum velocity where it would rest, okay? Where it's 0 here, that would be the equilibrium point. It's going to be fastest when it's going through that point, okay? speeds up, slows down, and reaches its top point. So it speeds up, reaches its bottom point, speeds up, reaches its top point, speeds up, and then slows down, reaches the bottom point, and so on and so forth. Okay, a little bit more than the problem asked for, and we can actually find that those values are going to be, let's see, looks like at 3 pi over 2, all right, the way cosines work, we got 0, pi over 2, pi, 3 pi over 2, 2 pi, so 3 pi over 2, and then again at 7 pi over 2, and then again at 11 pi over 2, it's going to reach its maximum velocity. All right, one last application problem. This happens to deal with a simple electrical circuit. All right, I got a diagram over here to the right. Shows a simple electrical circuit. If the capacitance is 1 farad, and the inductance is 1 henry, and the impressed voltage is 2t squared volts at time t, then a model of the total charge, Q of t, in the circuit at time t is measured by this function here. 2 sine of t plus 2t squared minus 4 coulombs. All right? If I butchered some of those physics words, I apologize. Didn't have the best physics teacher in high school. All right? Now, whether you understand any of that or not, totally fine. If you do or do not, let's read the rest of it. The current is defined by the rate of change of the charge. All right, rate of change. We're graphing it. Rate of change is similar, pretty much the same thing as the word slope. And slope, as we know, or rate of change, is going to be the derivative. Notice here the I, which is the current, is measured in the change in the coulombs, the change in the charge over the change in time. The dq over dt, and that's just a fancier way of saying the derivative of q at time t. All right? So, all we have to do here to compare the current at times t equals 0 and t equals 1 is first off, let's find the current function by finding the derivative of the charge. So if the q of t, again, the t stands for time, so get over it, 2 times the sine of t plus, notice how my t and my plus look totally different, plus 2t squared minus 4. All right, to find, what are we calling it? The current. All right, that's the dq over dt, the change in the current, or change in the charge over the change in time, which another way of writing is the q prime of t. So just find the derivative. So let's do it. The 2 is my coefficient. The derivative of a sine is cosine. All right, this one should be easy. That's just a power rule. The 2 comes down and multiplies by that 2 to become 4. And I subtract 1 from the 2 exponent to become 1, or I don't even have to leave it, write it out. And then the minus 4, a constant, its derivative is 0. All right, so this is the current formula here. All right, the change in the charge over the change in time. So let's answer the question. I want to compare the current at time 0 and the time 1. All right, so the I of 0 is the q prime of 0, which just means plug a 0 in there. So you have 2 times the cosine of 0 plus 4 times 0. And you got to remember some of your trig stuff. All right, the cosine of 0, cosine looks like this. So at time 0, cosine is at 1. So this turns into 2 times 1 plus 0, or just 2. All right, and to answer the other part, if I want to find the current at 1, I find the derivative of the charge at 1, which means plug a 1 in. So 2 times the cosine of 1 plus 4 times 1. All right, and 1 is not one of the ones we memorized. Okay, we memorized the pi over 2, 3 pi over 2, pi over 4, stuff like that. So you're going to need to grab a calculator. All right, I'm just using a TI-30X 2S, but you can use your graphing calculator. Make sure it's in the radian mode. So I'm changing my calculator to radian mode. In fact, your calculator really should always be in radian mode for calculus. All right, so if I say 2 times the cosine of 1 plus 4 times 1, or just 4, I get the answer of approximately 5.081. All right, so let's compare. At time 0, the current's 2. At time 1, the current is 5.081. All right, so if you want to know what kind of percentage that is, okay, what's the percentage change, we could do that. All right, I might tell you that in class. I'll have my book on me, make sure I'm doing exactly what they say. But that's it. Okay, we can compare them. They're compared. All right, well, that's the end of this video. Okay, the last slide here, you have the problems to try. I didn't give you any application problems. We'll do those in class. Then over here, when you actually get your sheet, will be the links to the YouTube videos which you're watching now. All right, hope this helps. If not, see you in class. Or I'll see you in class regardless. And coming back over, and bye.